Okay, welcome to lecture 12. We're still on unit 2, higher order ODEs. And so in the previous class, we learned that if we have an nth order linear homogeneous ODE, and if we have n solutions to that ODE, then we can check if they form a fundamental set of solutions by calculating the Wronskian. Okay, and if the Wronskian is not equal to 0, then that set of solutions is linearly independent and is a fundamental set of solutions to the ODE. And if we have a fundamental set, the superposition of those solutions, or you could say the linear combination of those solutions, that forms what we called a general solution. Okay, and so everything we did in the last class was for homogeneous ODEs, homogeneous equations. So before we move on, I wanted to touch on what happens for non-homogeneous equations. Okay, we're going to solve some non-homogeneous equations later in this class, but just as an introduction, let's look at how things differ when we have a non-homogeneous equation. Okay, we're going to look at three things: non-homogeneous equations, complementary functions, and then a method called reduction of order. Okay, and the reduction of order is going to give us one of those n solutions to our nth order ODE. Okay, so let's consider the nth order non-homogeneous linear ODE. Okay, so on the left hand side, if you recall, this is our linear differential operator, which essentially represents all the derivative terms and the linear term depending on y. So this is essentially our differential equation on the left hand side here. And on the right hand side is our term that has no y dependence. Okay, so again, if this g of x is 0, then this equation is homogeneous. If it's non-zero, then we have a non-homogeneous linear ODE. Okay, so any function which we're going to call y of p, y sub p, still a function of x, any function that is free of arbitrary parameters, so it doesn't have any constants in it that we don't know. So any function y of p that's free of arbitrary parameters that satisfies this ODE, this non-homogeneous ODE, is said to be a particular solution to this ODE. Okay, so well, the sub p, the yp, obviously the p stands for the particular solution. Okay, so any function that satisfies this nth order non-homogeneous linear ODE, we can call that a particular solution, and the particular solution has to be free of arbitrary parameters. So that means that when we're solving initial value problems, all our arbitrary parameters are going to come from the a homogeneous part. Okay, but we'll get to that in a second. So the general solution of a non-homogeneous equation. So we had the general solution of a homogeneous ODE, and that was we took the superposition of a fundamental set of solutions to the ODE. Okay, for the general solution to a non-homogeneous ODE, let y of p be any particular solution to the nth order non-homogeneous linear ODE on an interval, and let y1, y2 through to yn be a fundamental set of solutions to the associated homogeneous equation. Then the general solution to the non-homogeneous ODE is quite simply the sum of those things. So if we had a fundamental set of solutions to the homogeneous equation, so if this equation was a 0, L of y equals 0, then we could ignore this yp, and the general solution to the homogeneous equation would be c1, some constant c1 times y1, plus some constant c2 times y2, plus blah blah blah, plus some constant cn times y of n. This linear combination, or this superposition of solutions, is exactly the solution to the homogeneous equation. Okay, but because we have a non-homogeneous ODE, now we have this little extra term here, plus y of p, where y of p is some particular solution to this ODE. So the key points here is that this term that I've circled in red is the solution of the associated homogeneous ODE. So here to get the solution, we solve L of y equals 0. The extra part that we haven't seen before is a particular solution to this non-homogeneous ODE. So with the right hand side equal to g of x. So this is quite a powerful theorem here, the general solution of a non-homogeneous equation, because it says that we can break up this general solution into two parts. Firstly, we can find this term that depends on all these arbitrary parameters c1 through cn. We can find that just by solving the homogeneous version of this equation. So basically pretending g of x equals 0. We can solve that equation and find a solution to the homogeneous ODE. Then all we have to do to find the solution to the non-homogeneous ODE is add a particular solution. Okay, I haven't told you how we're going to do all this yet, but at least I hope the idea is clear, that we can form the general solution to the non-homogeneous equation in this way. Okay, but we should prove what we've said here about the general solution to a non-homogeneous equation. So we're going to let capital Y of x and y sub p be particular solutions to the homogeneous nth order linear ODE. L of x equals g of x. So these functions y, capital Y and yp are particular solutions of this non-homogeneous equation. Okay, so I know that if I take L of y of x or L of yp, that I'll get g of x back. So let's form a new function now, which I'll call u, which is just the difference between these two functions, both of which individually satisfy this ODE, this non-homogeneous linear nth order ODE. Okay, well if I operate on this function u with our linear differential operator L, so I apply u to L, then I get the linear differential operator applied to y, capital Y minus the yp, okay, which by linearity of the differential operator is just L of y minus L of yp. Because recall this L, this linear differential operator, is equal to, is linear. Okay. Now because both y and yp both individually satisfy this ODE, I already know that L of y is equal to g of x. And I already know that L of yp is equal to g of x, so therefore I just have g of x minus g of x equals 0. Hence, this thing u is a solution of the associated non-homogeneous problem. Okay. We can write u in this way: c1 times y1 plus c2 y2 all the way up to cn times yn, and we call this u actually the complementary function of the ODE. Okay, so here's another terminology you need to remember, make a note of. Okay, and so often we write the general solution of the non-homogeneous equation. So y of x is the general solution of the non-homogeneous nth order linear ODE. We write this as the sum of two parts. The complementary function, which simply solves this equation L of y equals 0, so the homogeneous part of the equation, the associated homogeneous equation, and this particular solution y of p, which is a particular solution to the non-homogeneous equation. Okay, and we know that y of c can be written as the superposition of the fundamental set of solutions to the homogeneous equation. Well, this should be to the homogeneous ODE. Okay, so there's a typo here. This non should not be there. Okay. So let's look at an example here. So I've got the linear differential operator, which is associated of a third derivative of y minus 2 times the second derivative of y minus y prime, the first derivative of y, plus 2y. okay? And we've got a function g, which is just a, well, it's polynomial 2x squared minus 2x minus 4 minus an exponential, so minus 24e to the minus 2x. And we're saying that when we apply this linear differential operator to y, or this first line up here, we get that is equal to, if you evaluate that, is equal to g of x, this function, this polynomial subtracting an exponential. We're asked to find a general solution on the whole real line. Okay, well, I'm going to tell you a few facts here that we can't calculate these ourselves yet, but later in future classes we're going to learn how to find these particular solutions. I'm going to let you know that yp1 equals x squared is a particular solution to this function, this part of the function 2x squared minus 2x minus 4. Okay, so this first part of g here, x squared is a particular solution to this sub-differential equation. Similarly, we can write yp2, so a second particular solution, which is equal to e to the minus 2x, is a particular solution to the ODE L of y equals negative 12 e to the minus 2x. So that looks very similar to our term here. Negative 24 e to the minus 2x is just a factor of 2 missing. And I'm also going to tell you that y1, y2, and y3, y1 being e to the negative x, y2 being e to the x, and y3 being e to the 2x, is a fundamental set of solutions to the homogeneous equation here. This linear differential operator L equals 0. y1, y2, and y3 is a fundamental set of solutions. So let's imagine I've calculated the Wronskian for this set of solutions, and that Wronskian was not 0, therefore we had a fundamental set of solutions. Okay. So we know that this solution to the non-homogeneous ODE can be written as the sum of the complementary function and the particular solution. Okay. And since we're given a fundamental set of solutions by part C here to the homogeneous ODE, we know that we can write y of c, the complementary function, as the superposition of these three functions. So in other words, y of c is equal to c1 e to the minus x plus c2 e to the x plus c3 e to the 2x. Okay, so we know that because we are told that this is a fundamental set of solutions to the associated homogeneous ODE. Okay, we also know that L of yp1 is 2x squared minus 2x minus 4. L of yp2 is negative 12 e to the negative 2x. Okay, so this term here on the right hand side of LP1 is exactly equal to this part of the function g of x. This term L of yp2 is half of the remaining part of g of x. But we know that these linear differential operators are linear. These differential operators L are linear. So I know that if I wanted to create a new linear differential operator, I can simply add these together and multiply by constants, and they simply operate term by term. So in other words, if I let a1 equal 1 here, and I let a2 equal 2, then I'm going to get a1 being 1 is LP1 is just this part here, and if a2 is 2, then I get 2 times this bit here, so I'm going to get negative 24 as required. Therefore, L of yp1 plus 2yp2 equals 2x squared minus 2x minus 4 minus 24 e to the minus 2x. Okay, so that is exactly the right hand side of the non-homogeneous ODE, or is exactly equal to this function g of x. Okay, so therefore I can write my general solution to the ODE as the complementary function yc here with the arbitrary parameters c1, c2, and c3, plus x squared plus 2 times e to the negative 2x. Okay, so remember I multiplied L of yp2 by 2, a2 was 2, which is where this 2 comes from here. So just to make it clear, this part in green here is the complementary solution, which comes from solving, it came from solving the homogeneous ODE, the associated homogeneous ODE. And the particular solution here is this extra part, which has no arbitrary parameters. Okay, that's a key point there. Okay, so this was really just an introduction to say that we can do something with non-homogeneous equations. We spent the last class discussing theorems about homogeneous nth order linear ODEs, but we can do a lot with non-homogeneous nth order linear ODEs as well. We are going to come back to non-homogeneous equations once we've learned how to solve homogeneous version, the homogeneous version. Okay, because as yet we haven't learned any techniques to actually solve these equations. We've just learned some theorems about them, some theory, some background stuff that we need to know about nth order linear ODEs. So the first method we're going to learn to solve, in fact, second order homogeneous linear ODEs is going to be called the method of reduction of order. So consider this homogeneous linear second order ODE and what we're going to call the standard form. Okay, so it's clearly linear, right? Because all the functions multiplying the y terms, the second derivative of y, the first derivative of y, and y, all these functions are functions of x only. So clearly this is a linear second order ODE. It's clearly homogeneous because the right hand side is equal to 0. And it's clearly second order, right? Because the highest derivative is 2. Okay, so we're going to let y1 be a non-trivial solution to the ODE. So what I mean by non-trivial is I'm saying y1 is not equal to 0. Because if you think about it, the solution y equals 0 solves this ODE, right? Y equals 0, derivative of 0 is 0, second derivative of 0 is 0. So, well, we don't really care about the trivial solution. Let's look for a non-trivial solution. Okay, so imagine somebody hands you a non-trivial solution to this ODE, which we're calling y1. Okay, and says, well, this is a second order ODE, so to form a fundamental set of solutions, we need 2 solutions to this ODE. Okay, and in fact, 2 linearly independent solutions to this ODE. Okay, so we want to find a second solution, y2, by using a separate first order equation. So somebody gives me y1, somehow they know what this one solution to this ODE, and I say, okay, well, if you give me 1, I'll give you the second one. That is what this method does. Okay, so we're going to go through the derivation of this method, and at the end will be a summary basically of how you apply this method of reduction of order. Okay, so we're going to let y2, the extra solution we're trying to find, be the product of 2 functions. One function u of x, which we don't know, and one function y1, which somebody's given us. So we know y1. Somebody's given us that y1 is a solution, so we know it. We do not know what u is. We're trying to find it. U has to be a non-constant function. It can't just be a constant. It has to be a function of x, because if it was just a constant function, y1 and y2 would be linearly dependent solutions, and well, that does not give us a fundamental set of solutions. Okay, so let's take the derivative of this equation here, this y2 equation, with respect to x. So on the left hand side it's quite easy. Y2 is just y2 prime if I take the derivative. But the right hand side I've got 2 functions of x multiplied together, so clearly I'm going to get a product rule. So if, let's say initially I hold u constant, I'm going to get u times y prime, y1 prime. plus, holding y1 constant, u prime times y1. So u2 prime, the derivative of y2, the derivative of y2 is equal to u times y1 prime plus u prime times y1 by the product rule. Okay, well let's take a second derivative now because we've got a second order equation. If I do that, again I'm going to get a product rule, so I'm going to end up with 4 terms here because I have 2 terms from this first product, u times y1 prime, and then I have another 2 terms from u prime y1. Okay, so well, what is this going to be? I'm going to get something like u times the second derivative of y1 plus u prime times y1 prime. Okay, that's from two terms from this first part here, plus u prime y1 prime plus u double prime y1. Okay, so I'll get 4 terms here. So y2, the second derivative of y2 is given by this equation, and that's found by applying the product rule twice to the y2 prime. Okay, the 2 terms in y2 prime. Okay, well I can simplify that, of course, because these 2 terms in the middle here are exactly the same, so I'm just going to get 2 of that thing. So y2 double prime is equal to u times y1 double prime plus 2 times u prime y1 prime plus u double prime y1. Okay, so now we're going to take these expressions and we're going to use these in the ODE, in this second order homogeneous linear ODE. Okay, so well, there's a bit of algebra here, but y double prime here is going to be equal to this bottom line here. Okay, the second derivative. Okay, so here we have u y1 double prime plus 2 u prime plus y1 prime plus u double prime y1. Okay, so this first term is quite simply the second derivative of y2 plus p of x times y prime. Okay, but y prime, for y2 prime at least, we found this expression u times y1 prime plus u prime times y1, so you see that here, plus q times y. Well, y in terms of y2 is just simply u times y1, so we have u times y1 in here, and of course that whole thing has to equal 0. Okay, well, I can do a little bit of algebra on this long equation here, and I can write it in this form by taking out the common factor of u and u prime in some of these terms. So wherever we see a u, I'm going to pull out this common factor of u. So see, I've got a y1 double prime here, so that enters here. There's no other u terms here. They've got a u prime and a u double prime. Here we've got another u, so we've got u times y1 prime times p of x. So in here I have a p of x times y1 prime. This is not a u, it's a u prime. And then finally I have q times u y1 here. So I'm going to have a plus q times y1. So I've just pulled out that common factor of u. I've got the common factor of u double prime here, which only actually appears once in this above equation. And then I've also pulled out the common factor of u prime, which appears twice. So you can find that in the above equation. But the key thing to note here is that y1 is a solution to this ODE. So if I write out y1 double prime plus p of x times y1 prime plus q of x times y1, that equals 0. That does equal 0 because y1 is a non-trivial solution to the ODE. Okay, but that is exactly what I've got in this term here. So in fact, this term here we know is equal to 0 because this term is exactly, looks like the left-hand side of the ODE, and because y1 is a solution of the ODE, we know it must be equal to 0. So this term happily disappears. We get left with something that is a lot more tractable. We get left with just these terms over here that are not crossed out. Okay, so let's write that down. This is all we get left with. Yeah, good. So now we need to try and solve this equation. Okay. So the method of reduction of order, continuing on, we're going to make a substitution, okay? So if we make the substitution, so this is the equation in red here, in the red box. I've just rewritten it at the top here so I have more space. If I make the substitution w, a new variable w, equals u prime, I can rewrite this equation, okay? Because if you think about it, the derivative of w is going to be u double prime. So what I'm going to get up here is y1 times the derivative of w, so w prime, plus 2 times y1 plus p of x, y1, times w equals 0. Okay, like so. So now this is a separable first order equation in this new variable w. Okay, so w prime is dw by dx. So let's rearrange that equation. We get dw by w minus 2 times y1 prime over y1 dx minus p of x dx. So how do I get this? Well, I take all the terms apart from w prime over to the right hand side. So I get negative 2 y1 minus p of x times y1. And then I divide through by y1, the y1 that's multiplying w prime. Okay, and then w prime is dw by dx, so I multiply through by dx, and I divide through by w. So I end up with, well, okay, do the algebra, and if you're unconvinced, let me know. This is the equation that I need to solve this separable ODE. Okay, so I've got to evaluate some integrals here. So this integral in the middle here, this integral, the first integral on the right hand side, this actually we can write in a new way. So this integral here, negative 2 times y1 prime over y1 dx, we can actually write that in a slightly different way, because if you think about it, y1 prime is equal to dy1 over dx. So if instead of writing d1 prime, I write this explicitly, dy1 over dx multiplied by dx, well, these dx terms, these differentials cancel out. And so we just end up with negative 2 times the integral of dy1 over y1. So then really all I'm integrating is 1 over y1 with respect to y1, which of course is really simple, it's just a logarithm. So we get negative 2 times the log of y1. And of course we can use our lovely log laws and say that, bring this 2 into the exponent here, and I can just say this is equal to negative the log of y1 squared. Okay, so I can evaluate these integrals now. Well, the left hand side dw divided by w is just the log of w. This term I've just set, this term in red I've just set as negative log of y1 squared. And well, the integral of p of x I don't know. It depends on what kind of function p of x is. This could be a polynomial, it could be an exponential, it could be a rational function. It's really context dependent. And of course, well, we can't forget our friend the integration constant plus c naught here. Okay, so I can rearrange this equation using log laws, okay? So by log laws, I can rewrite this by taking this negative log of y1 squared. I can move that over to the left hand side by adding the log of y1 squared, and then I can combine the two logs using the log laws, okay? So the log of a plus the log of b equals the log of a times b. So therefore on the left hand side I get the log of w times y1 squared equals the negative of this integral of this function p, which again is problem dependent, plus our arbitrary integration constant. I can get rid of this log on the left hand side by taking exponentials. Okay, so I end up with the absolute value of w times y1 squared equals the exponential of all this thing here. And again, I can simplify the plus c naught by again using the laws of exponentials. And so what I'm going to do is I am just going to simplify this equation by saying C1 is equal to plus or minus the exponential of C0. Okay, so W times y1 squared equals C1 times the exponential of this integral of this function p of x. I can divide through by y1 squared to get the solution in terms of W. Okay, so W equals some constant C1 over y1 squared times this exponential. Okay, and now we can recall that the definition of W is U prime, okay? So W is equal to U1 prime. So in fact, I could actually write U is the integral of W, okay? So U is the integral of W. A further point that we should note is that y2 is simply u times y1. So therefore, I can write an expression for y2. y2 is just y1 times u. U is the integral of w, and w is this thing. So if I put this all together, y2 is equal to y1 times the integral of w, where w is this thing here. So y2 equals y1 times the integral of w. Okay. So my integration constant here is no longer required because, well, we're going to potentially get another integration constant in this equation. But in fact, that will not change the solution at all because we're just going to be adding a constant to our solution y2. So, well, we've now actually derived a new solution y2 from this first solution y1. Okay, so I really just want to summarize this here. If you didn't quite follow the method that I've just gone through to derive that second solution, please check the textbook, maybe watch this again, but read the textbook too. But if you only remember one thing from the last 15 minutes or so, remember this slide here. If we have a homogeneous linear second order ODE in the standard form, so homogeneous linear second order, and we're told that y1 is a non-trivial solution to the ODE, somebody gives me a solution to this ODE, then I can always find a second linearly independent solution by calculating y2, or defining y2 as so. Okay. So remember, somebody has given me y1, so I know what y1 is. P of x is just the term in the ODE, which is multiplying y prime, so I know what this is. So as long as I can evaluate these two integrals here, I can always find the second solution. Okay. If we have one solution to the second order linear homogeneous ODE, we can use the above equation to find a second solution, and the second solution is always linearly independent of the first. Okay, so let's just finish this class off with an example. So consider the second order linear ODE, homogeneous ODE, y double prime minus 2y prime plus y equals 0. Clearly it's linear, clearly it's second order, clearly it's homogeneous. Somebody comes up to us on the street and tells us that y1 equals e to the x is a solution to this second order linear homogeneous ODE. Determine a second linearly independent solution using our method of reduction of order. Okay, well, let's just identify these terms here. P of x equals -2, that's the term that's multiplying y prime. Q of x is 1, that's the term that's multiplying y. From the method of reduction of order, we know that we can find a second solution from the first by solving this equation here. Okay, so therefore y1 is equal to e to the x, p of x is equal to -2, so our equation becomes e to the x multiplied by the integral of the exponential of, negative the exponential of -2, so we just get the positive exponential of 2, the exponential of the integral of 2 dx, divided by y1 squared. So if we square y1, we get e to the x all squared, which is equal to e to the 2x dx. So of course this first integral in the exponential here is really easy. It's just, integral of 2 is just 2x, of course. So we're going to get y2 equals e to the x times the integral of e to the 2x over to e to the 2x. Okay, well, that's easy, right? That's just 1. So now we just get simply e to the x times the integral of 1 dx. Well, the integral of 1 dx is just x, right? So y2 is equal to x e to the x plus our integration constant times e to the x as well. So we do need that integration constant when we calculate our second solution y2. So this is a second linearly independent solution to the ODE, and really this is true for any value of the integration constant. So, well, maybe we don't need the integration constant because we can choose this integration constant to be any number, so let's just choose it to be 0. Okay, so the method of reduction of order is going to crop up in a later class. It is something that you need to know. It is something that will pop up in the first assignment. So I hope that if you remember nothing else, remember that if I'm given a solution to a second order linear homogeneous ODE, then I can always find a second solution using the method of reduction of order, which summarizes just this integral here, or this equation here. Okay, thank you very much. I'll see you in the next class.